All right, problem one. So we are looking for the sign of work on the comet by the star at different locations. So we know work is the dot product of the force vector and the displacement vector. So let's take a look at some different spots. At point D here, look at point D, what is the force vector going to look like? We know gravity pulls in a straight line, so that's going to be our force vector. And then our displacement vector is going to be, it's going in a direction around in the orbit like that. So it's going to look something like that. And let's make some dummy vectors here. So let's say this is the y direction here, x direction there. Our force vector then, let's just say it's 1, 0, 0, kind of looks like that. And then dotting our displacement vector looks something like 0, -1, 0. And then the way we take our dot product, you multiply each of the same components and then add them up. When you do that, you get 1 times 0, 0, plus 0 times -1, 0, plus 0. So our WD is going to be 0. If we do the same thing at A, that will be our displacement vector, force in that direction. So the work at point A is also 0. Okay, let's take a look at C now. So we know A and D are 0. Let's take a look at, let me get rid of all this. Okay, so we know A and D are 0. What's the force vector at C going to look like? It's going to look something like that. And then our displacement's going to be in that direction. So let me make some dummy example vectors again. So working at the C, it's going to be something like the force is, let's say, still have this. Y is up and down, X is left, right. Let's say 0, -1, 0, for example, dotted with -1, -1, 0. For this displacement, looks like it's going down to the left, so let's say that. So then work in the C is going to be 0 times -1, 0, plus -1 times -1, +1 is what our work at point C would be. So we know C is going to be positive. Let's look at B. Well, B, that's the force one, and then our displacement is going to look something like that. And work for D is also going to be, let's say, greater than 0. And the reason here is because the dot product is kind of a measurement of similarity of direction of vectors. So if the two vectors we're dotting are pointing in the same direction, you're going to get a positive work being done, as opposed to if they're pointing in the opposite direction, which is what we're going to have in E. So at E, gravity's that way, displacement is this way, and if we make some dummy vectors again, let's say our force is 0, 1, 0, displacement's going to be, what is that, 1 to the right, and it's going down, something like that. This is going to be 0 times 1, 0, plus -1. Oh. So -1. And then same thing for E, or for F. And this is because they're pointing in opposite directions, so you're going to get a negative work. So C and B are going to be positive. So C, B, those are greater than 0. We already know D and A are 0. And we got E and F less than 0, because the two vectors are going in opposite directions. So which one does that line up with? Let's see. Looks like B, which is correct. Okay. Ferris wheel is vertical circular amusement ride with radius r equal to 10. Riders sit on the seats that swivel to remain horizontal. The Ferris wheel rotates so that the riders move at a constant speed, which is 5 meters per second. Consider a rider with mass that, assume that the acceleration is 10. How much work does the force exerted by the seat do on the rider as they move from H to B? Okay, so as we're going to solve pretty much every problem in this test, we're going to need the energy principle. Delta E equals work, and let's set up our system and surroundings. System, let's say person, Earth. You could put the Earth in either one, but it's easier to put in the system, or less room for confusion if you put in the system. So let's do that. And then our system is going to contribute to the left-hand side of the equation. Work's going to contribute to the right. So on our left-hand side, we're going to have delta K trans plus delta U gravity, which is equal to the work. And since the seat's the only thing in our surroundings, it's the only thing that can do work, so I'll call that work seat. And if we compare here, we know that delta, you're going to get final minus initial. So this would be 1/2 mvf squared minus 1/2 mvi squared plus, okay. And then for our gravity here, we're going to be comparing point H to point B. So let's say arbitrarily, say this is H equals 0, and we know that the radius is 10 meters. So at this point is H equals 10 meters. That is not an M. Okay, H equals 10 meters. So the final position, we're going to have mg 10, and then we're going to be minusing the initial, which is mg 0. And that's going to be equal to work done by the seat. Okay. Let's also make another observation that you're going to be going around at constant speed the whole time. So Vf equals Vi. This whole term is going to be 0. There's no change there. So what does this simplify to? 10 mg equals work done by the seat. And we know, what do we know? We know G is 10, obviously. M is 60. 10 times 60 times 10, 6,000. There we go. Which is correct. Okay, problem 3, we got a coding problem. We got motion of an object attached to a spring moving along an inclined ramp. So let's try to picture this real quick. Inclined ramp, something like that. Maybe you got like a wall there. Oh God, that is not a good spring. Okay, something like a spring, object at the end. Just from doing the test, I kind of know what we should think here. Let's do a force balance on this spring. So obviously, it's going to have mass, so it's going to have a force of gravity right there. Springs always pull in line with the direction they're facing in, so there's a force due to the spring there. And then there's also one more force. The ramp is going to push a normal force on the block there. So if we go through just line by line, some of these look okay, they look decent, they look good. And then when we get down to this line, we notice there's an F spring, that's good, we had that. There's an F gravity with that one, but they don't have the normal force. They need a plus F normal. So that looks like an issue right there. And that corresponds to B, which is correct. Okay. Problem 4. A spacecraft with, let's draw a spacecraft. Okay, mass 100 is in outer space at location 1, moving with speed initial. Thrusters turn on, they put a normal force on for some distance, and then thrusters turned off, and another set's turned on for another distance. Okay, what is the speed at the final location? So we're going to need to do energy balance here. Delta E equals work. Let's set up our system and surroundings so we know where to put everything. Let's put the spacecraft in the system. And then surroundings, let's do the force by the thrusters. That's going to want to be in our work. Okay, so let's see here. Okay, so in our spacecraft, actually write that out. It's going to have kinetic energy, right? In a part of our system. Let's see here. our delta E, it's usually comprised of a couple things. You got kinetic energy, potential, maybe like spring. It can be comprised of all of these things. The only relevant one in this problem is going to be our kinetic energy, so we can just ignore everything else. So delta K trans equals work. We can set that up. So therefore we can say this, half mv final squared minus half mv initial squared equals work. And I'm going to call this work total. Reason being, we're gonna want to sum the two different works. So let's say the thrusters turn on initially, and then it takes our spaceship over here, and then a different set of thrusters gonna be turned on, and it's gonna be down there. We can calculate the total work by simply adding up these contributions. So let's call that work 1 and then work 2. And we also know that work is equal to the dot product of force and distance. There we go. So let's calculate each one of these first. Work 1. Okay, work 1, our force vector, as they tell us, that's just negative 100, 200, 0, dotted by our displacement vector. How are we going to get this displacement vector? Let's do that over here. You're going to subtract the final position vector minus the initial. So 235 minus 125, and that's going to give us 110. Okay, and let me give a little graph to maybe show what we're doing. Oh, okay, so we start at 2, we'll call that 2, 3. I'm going to ignore the z coordinate because it's the same. And we're moving to, oh wait, that's where we end up. Okay, we started at 1, 2. We started there, and we're going up there. So if we just subtract those, we get the displacement vector, which is our d that we need. So d1 is going to be 1, 1, 0, and then let's get d2. We got the final position 5, 4, 5, minus where we just were 2, 3, 5. d2 equals 3, 1, 0. There we go. Let's put in the force. The force for the second period of thrust is 200, negative 100, 0, dotted with 3, 3, 1, 0. Okay, and we're going to take the dot product, multiply each component together, and then add them. So negative 100 times 100, negative 100 plus 200 plus 0. That's going to equal 100. This one, 600 minus 100 equals 500. Okay, so now we just got this, we got that. We got work 1 and work 2. I'm going to pull this equation back down now. Half mvf squared minus the initial kinetic energy equals 100 plus 500. Okay. And let's see, what else do we know? We know mass, we know velocity initial. We want to find VF. So let's do that. What's our mass? 100? Yeah, okay. Half times 100 VF squared minus, I'm just going to half times 100. What's our initial velocity? Initial velocity is 2 times 4 equals 600. So 50 VF squared minus 200 equals 600. VF squared equals, what's 800 divided by 50? Okay, I can't think right now. It's 16. Okay, and then VF equals 4. So let's see. We got a final velocity of 4 meters per second, and that looks good. All right. Problems 5 and 6. Here we go. So we got a block of ice, mass m. It's initially at rest, so V initial equals 0. At location 1 on a smooth semicircular track, and it's later sliding. Okay, so we want the speed at location 2. We're comparing position 1 to position 2, so we can do a energy balance here using our energy principle. Let's decide on our system and surroundings too. So in our system, let's put the block, and I'm going to put the Earth in our system because it usually leads to putting the Earth in the system generally makes getting the sign right easier. Sometimes if you put it in the surroundings, you can get the sign wrong. It makes more room for error. Perhaps in our surroundings, let's put the ramp. Not that it's going to matter. Okay. So now let's set this up. Our energy of our system is going to be comprised of K trans of the block, and then U gravity, right? Potential gravity. So that's going to look something like this. Half mvf squared minus half mvi squared plus, okay, let's see what our positions are going to be with respect to h. Let's call this h equal to 0. Oh, and we have a radius. So we know this radius is r. We can call that height r. So finally, we are at mg 0. At the final position, we are at a height of 0 minus mg. Initially, we're at r. And the only thing in our surroundings that could do work is the ramp. The ramp's not going to do any work on our system, so work is 0. I'm going to change that to none, actually. Okay, so work is 0. So we have our balance set up here. We know that Vi is equal to 0, as I said earlier. That term is 0. Mg times 0, that's 0. So we get half mvf squared minus mgr equals 0. And then we can add over mgr. Half mvf squared equals mgr. You got m's on both sides. Those can go away. And wait, what are we trying to solve for? We want v. We want vf. So times over 2 vf squared equals 2gr. Vf equals root 2gr. There we go. So that leaves us with B, which is correct. Okay. Magnitude of normal force exerted on the block. Okay, so whenever we have a semicircle track, or whenever we have something moving in a circle, in a circular motion, we know that the net force is always going to be equal to mv squared over r. This is always true when we're moving in a circle here. You're going to get there's a couple variations of this problem they could give you with maybe like a truck moving in a circle. I've seen that one. But you need to know this fact for this problem. So they want the normal force. So what is our net force comprised of? Net force is always just the sum of the forces acting on our object. So let's do a force balance on our block down at position 2. Let me clean this up. All right. At position 2, you got gravity, obviously. The block has some mass, so you're going to have gravity pointing down. And then also the ramp is going to be pushing up on the block with a normal force. And we know that net force is equal to mass times acceleration. The block is accelerating up, so therefore we know the normal force has to be greater than the gravity to accelerate it in that upwards direction. So, let's see. Our net force is going to be Fg plus Fn, and we know Fg is equal to mg. So we can sub this all in. Okay, Fn plus mg equals mv squared over r, and we solved for for r, can't speak, for v previously, so we can use that to substitute in. So we got normal force is equal to mv squared over r minus mg, and we know up here that v is equal to root 2gr. So then this is going to become Fn equals 2, actually I'll do this, oh, yeah. M square root 2gr squared over r minus mg, which the square of a square root is just going to go away. So you got 2mgr, that is a terrible r, 2mgr over r minus mg, and I already see where we went wrong. This normal force is pointing up in the positive y direction, F of g is going in the negative y direction, so I should have made that negative. There we go. That should have been negative. This becomes positive. There we go. Okay. Slight correction. Gravity's pointing in the negative direction, considering we're saying g would be positive here. So gravity's going to be pointing in the negative direction, and then you add that over, that gets you positive. Yeah, okay. And then r's cancel. And if we simplify this, normal force is 2mg plus mg. That equals 3mg, which leaves us with C, which is right. Okay. Okay. Radioactive mass, radioactive nucleus, M1, is at rest. Whenever we got problems like this, too, rest energy is equal to mc squared. We're going to need that. It decays into two of these. And eventually they move far away from each other so that they're not interacting. So, let's just say very far. Whenever something's very far away, they just mean the potential electric energy is going to be completely zero. So, let's set up our energy principle. Delta E equals work. And let's say system, surroundings, none in the surroundings. System are going to be our particles. Okay. So, let's say, okay, so this is going to be, since there's nothing in our surroundings, let's say delta E equals 0, and then by extension, initial energy equals final energy. So we can find out what our initial energy is, we can set it equal to our final. Okay, so what is our initial energy? The only initial energy we have is the rest energy of this particle. So m1c squared equals the final energies. When they're very far away, they're going to break apart and then be moving with velocities. So, here we go. Finally, they're going to have, let's say, k-trans of the alpha particle and then k-trans of the second particle. They're kinetic energies, but there's also they have their own rest energies as well. Okay, hold on. Hold the phone. Okay, mass alpha c squared. There we go. So, initially, this first particle isn't moving. It has no translational kinetic energy. The only energy initially there is going to be its rest energy. Finally, after we split into the alpha particle and the second particle, they're going to be really far away, so they have no electric contribution to energy. They both have kinetic energy contributions, which would be half mv squared, as well as their rest energies. So that's our energy principle right there set up. And they're asking for the sum of kinetic energies, which is essentially just this. So if we want that term, we can just subtract over the others. So k trans of alpha plus k trans of 2 m1 c squared minus m alpha c squared. That's also going to be minus m2 c squared. There we go. And that leaves us with answer choice D, it looks like, which is good. Okay. All right. Problem 8. The figure below is a graph of the energy of a system consisting of a planet interacting with a star. So, planet, I'm not going to label it. Oh, God. That's a star. Okay, and they're interacting. They have kinetic and potential energy contributions. So our energy of the system is going to be U grav plus kinetic. Okay, and let's see here. The first question they ask is kinetic energy decreases as the distance from the star to the planet changes from R1 to R2. So we know this is our potential energy line. And as we change, we know that, okay, so let me say this. Oh, my Apple Pencil's breaking. All right, we know that this is our total energy line. So as we change from R1 to R2, potential energy is, it's increasing, right? We're going up here. As we move from this point to this point, we have that much potential energy increase. So if our U grav is increasing, what has to happen to kinetic? It's got to go down, right? Because our energy of the system isn't changing. So that's true. Number 2 says the exact same thing but increases, which we just proved couldn't be true. And then when the distance from the star to the planet is R2, get rid of my mess. When we're at a distance R2, kinetic energy equals A minus B. So like I said, oh man, my Apple Pencil is not working. Okay, this is our total energy line. This is potential. So let's see here. According to our equation up here, if we do energy of the system minus U grav, that's how we would get K tran, right? Or I guess it's just K. I'll just call it K. That's how we could get K, just pulling from what I said up there. The total energy of the system is at A, minus off at that point U grav is B, so that would be K, which is exactly what they say there. So 1's good, 2 no good, 3 good. The system is a bound system. The planet can never escape, which, if we look at our potential energy here, looks like this is like tangential to the to 0 here. So we're always going to have a non-zero potential energy. Oh my gosh. Which means that's true. So we got 1, 3, and 4. Therefore, we know it has to be C, which is good. Okay. Oh, my favorite. 3 protons in a triangle. Protons have positive charges. Okay. They each have mass m and charge plus E. They're held in a triangle, length D in sides. Okay, which of the following equations do you need to determine? So what they want us to do here is just do an energy principle balance on this. So what's in our system? What's in our surroundings? Let's put the particles in our system. Actually, we're gonna do this instead. We're gonna do 1 particle. No, actually we're not. We're gonna do all 3. All 3 particles are in 1 system. Okay, so initially, and we're gonna put nothing in the surroundings, which means nothing's in the surroundings, which means nothing can do work on our system. Delta E equals 0, which means EF minus EI equals 0. EF equals EI. Okay. When they move very far away, so let me try, I don't know, they're very far away, they're going with velocity. This distance is no longer d, it's infinity. So they're no longer interacting far away. Far away, the only contribution is going to be k trans. Yeah, k trans. And then initially, they're not moving at all, which they say they're released from rest. So initially, we only have U electric. So let's go ahead and set this up. Initially, or finally, we're going to have 3 particles moving away too. So we're going to need to times this equation by 3. F squared. And also initially, we're going to have the U electric as a measure of interaction between these particles. And we have 3 of those, right? We have 3 sides of this triangle. 1, 2, 3. So we're going to need a coefficient of 3 there as well. And then the equation for this, oh my gosh. The equation for U electric is this coefficient 1 over 4 pi epsilon naught times charge squared over d. And that should be our equation. Oh, and then they called QE. So that corresponds to A, it looks like, which is true. Okay. 10. An object attached to a spring oscillates back and forth on an inclined plane. The x-axis is parallel to the inclined plane. The equilibrium position is x. Okay, let's draw a picture. Turn that off. Okay. Okay, inclined plane. Something like this. It's oscillating. Let's see. Okay. Wall, maybe something like this. And it's going back and forth. Okay. At t equals 0, the object is released from uncompressed spring position. Okay. Uncompressed means that if it's uncompressed, we're in a unstretched spring state. So the spring is not going to exert any force initially, which means initially it's got to move this way due to gravity. So let me explain that a little bit better. Initially, our force due to a spring is the spring constant times how far it's stretched. Initially, there is no stretch, therefore there's no force the spring is going to exert. The only forces acting initially on the block are going to be gravity and then the normal force. Therefore, I know it's going to, therefore I know initially it's got to move to the right. It's going to have to accelerate to the right. So let's see. Okay, we're looking at graphs here. So I know initially it's going to have a velocity of 0. Let's do some process of elimination. Initially it's got to have a velocity of 0. No. And okay, the other 3 have starting velocities of 0. Okay. And it's going to accelerate with positive velocity. So no. Okay, so the only difference between these, man, my pencil. The only difference between these two is where the position starts. Well, actually, I suppose they follow completely different arcs. Okay, but okay. All right, let's follow our velocity. Let's see what this one looks like. So we have positive. Well, okay, this first one This first one up here really doesn't make any sense because we're going in positive velocity direction, but moving in negative x. That doesn't really correspond this whole time. Also, we're still moving. We have the same direction of velocity here. We would still be moving to the right. Anytime we're above this line right here, we're moving, say, to the right. say that's down the plane. This entire time from this point to this point, we're moving in the same direction. But this one shows actually a change of direction there. So that could not be true at all. Therefore, it must be E. All right, problem 11. A motionless light vertical spring, it's hanging with the mass. You pull it down, release it with some velocity. Which equations do you need to get max compression? Okay, this one's going to be tricky, I recall. So let's see here. This is an energy problem. Delta E equals work. Let's make our system and surroundings. Let's put the block in our system. Let's put the earth in our system, as well as the spring. None. So work equals 0. Okay. So let's start setting this up. We're going to have a delta K trans from the block, delta U gravity from the earth, and delta U spring from the spring. It's all going to equal 0. Okay. And we want to find S max. So we want to find that distance. So let's compare, let's use this as our initial, and this as our final condition. In the final condition, it's going to be at rest because it's at the maximum. So K trans final is going to be half M, and V is 0, so 0 squared minus, what's our initial? Half MVI squared plus, okay, so there's our delta K trans contribution. Now if we take a look at our gravity, let's make this H equals 0. Okay. So then in the final state, we're at mg max. That's how far we are above x. And then initially we are mg negative si, because we're down that far, that distance from h equals 0. And then I'm going to go to the next one here, plus our delta U spring. And if we don't remember, potential of a spring it's kind of analogous to kinetic energy. It's half Ks S squared, where K is the spring constant and then S is stretch. So let's take a look here. In our final position, what's our stretch going to be? And this is our stretch from this spot right here. So we are stretched that far. Okay. So what is that? Let's call this distance right here from the mass in the final position to this little arbitrary line we made earlier. Let's call that A. I'm going to call that A. So let me clean this up. This is getting messy. I called this A. We know the whole thing is S max. So if we wanted this distance, if we wanted the stretch distance, which is just this length right there, we can do S max minus A. So let's put that in for our stretch. Half Ks S max minus A squared. I just plugged it into this equation right here, and I said our stretch S final is equal to S max minus A. That's the stretch from our equilibrium position right here, stretch to that position right there. Okay. And then what is it going to be initially? So same coefficients. And we're going to have, looks like we're looking for the stretch between this point to this point. So what is that? We got A again, we got A contribution right there, and then plus SI. So that's how far we are stretched in the initial condition. It's, write that too, initial, S initial equals SI plus A. So there we go, we got SI plus A squared. That all equals 0. Okay, big term here. Let's see if we can do some simplifications. So this is our equation that we're going to start simplifying. Okay. First one, that's just going to turn into, I always like this, 0 minus half mvi squared plus mgs max plus mgsi. Okay, and then I'm gonna solve for these little binomials here. So that's gonna turn into half ks s max squared minus 2a s max plus a squared. God. And then we are going to get minus half ks si squared plus 2a si squared plus a squared. And then closed. So this whole thing is our spring now, is our change in spring potential energy. Okay, so let's try to simplify this a bit. We're going to need one more piece of information, actually. So right now we can't simplify anything, but we know how we could rewrite ks. So let me give you this something to think about here. If we just look at our unstretched equilibrium position of our spring, we can actually figure out what ks is. So what are the units on ks? The units on ks, and the brackets around equals just mean units. It's going to be newtons per meter. It's force per meter stretched. So if we compare our first condition here and our second condition, we know that in our second condition, the force being applied to the spring is going to be mg, and we're stretching a length si. So if we did, perhaps let me explain it this way too. If we did a force balance on this mass, you've got, oh my god, my pencil's going crazy. Oh god. Okay. You got a force of the spring pulling up, and then you have the force of gravity going down, and they have to be equal. Actually, this is not right. Okay. They got to be equal. So the force of our spring has to equal the force of gravity, which we know is mg. And we know the force of a spring is equal to ks times stretch. So ks times, what's our stretch here? Our stretch is a. The difference between these two, how far it's being stretched, is a. So ks times a equals mg. Therefore, ks equals mg over a. And that might become useful down here. So let me write that again. Ks equals mg over a. Okay. So now we've got this pretty mess. All right. I'm going to rewrite this really quickly. Okay. All right. So that's all rewritten. That's going to stay the same. And I'm going to distribute some of these into here with what we know about ks. Actually, I'll rewrite it one more time just so this looks better. Half, and now I'm making this substitution right here. Half mg a s max squared minus 2as max plus a squared minus half, what is it? Mg over a si squared plus 2a, that should not be squared. I don't think that should be a square right there. 2a si plus a squared. Okay, which all equals 0. Now I'm gonna, before I start simplifying more, I'm gonna let the answers guide us a little bit. So we know the right hand side has to equal 0 because we put nothing in our surroundings. So yeah, nope. Wait, that equals 0. That's fine. This one has something on the right hand side doing work, and so does this one. So it's not either of those two. Okay. And looks like if we're looking at their answers, looks like potentially mg is going to get canceled out. So let's see if that happens. And maybe it's just better to look at it and get the final answer first. So we should look for terms in this mess that could potentially cancel with those over there. And it looks like when we distribute this into that term, we could get some cancellation. So that would become mgs max. Yeah, that would cancel. So this term is going to cancel with that term, and that term, and then we got mgsi, which if you were to distribute that into there, you would get mgsi. So that's also going to go away. Let me cross that off there. I meant to just erase the arrow. Okay. So final. Oh, and then wait. There should be one more. Okay, let's rewrite some of the simplifications we just made. Vi squared plus, let's do this. I'm gonna do half. Let's distribute into there. I'm gonna say mg over a s max squared plus half, that'll be mga. mga. Yeah, because, okay. And then minus half mg over a si squared plus half mga. Okay, there we go. Now if we look at this, now we notice this term is going to cancel with that term. Goodbye. Final answer, here we go. Boom. Oh god, that's not 2. There we go. mga. Okay, also, remember that, one more substitution. Remember this, ks equals mg over a. That's why I left that in the parentheses. Half ks s max squared minus half ks si squared. All right, that's our answer. See, yeah. Yep. That looks like B. Okay. Yeah, I would say that's the most algebra heavy problem you'll see, because that one was kind of a mess. Remember though, you set up your energy balance. The tricky thing here is you had to make this substitution. You had to use the condition of these first two springs to figure out what ks was, and you could use that to cancel some of the gravity terms. That was a tricky thing about this one. All right. Problem 12. A woman lifts a barbell. Let's draw a picture. Everybody likes pictures. Woman lifts barbell. What's a barbell look like that? Her arms aren't touching it. Constant force, she lifts it and then it acquires speed. Finally, she's down here, and it's got velocity. Okay. And the woman has energy. We can use E woman to represent that. Awesome. So our system is going to be woman, barbell, earth. If all that's in our surroundings, I can't think of anything else to put in our surroundings. So delta E equals work. If there's nothing in our surroundings, work equals 0. Delta E equals 0. Okay. Okay, so here they don't really mention it, but if we want E woman in our system, we're looking at more of an extended system where we're not going to consider the work done by this. So reason being, actually let me run through what this would look like if we were a point particle system. Point particle on the barbell and how this would be different. Point particle on the barbell, we would have delta E equals work, and we would say that delta K tran equals, and gravity, plus, let me just write out what this would be actually. So finally you would have energy, half mvf squared, no initial. Finally it has mgh, no initial, I'll call that h equals 0. And the E woman wouldn't exist if we said this was a point particle. So then it would have FH. That's if we did the point particle, because the center mass of the barbell would move through that H with the force. But when we look at the actual, I'm just gonna erase this. When we look at the more extended system, which is what they're getting at, instead of having that FH, you're gonna have E woman. So let's include that in our beginning, and then the other part's gonna be the same. You're gonna have that same final kinetic energy, GH. Same with gravity, and then your work's gonna be 0. And why is your work gonna be 0? Considering the woman's in our system, the force is being applied here. Let me draw a little better. So those are her toes or her feet. The force is being applied on. Well, actually, it's going up. Oh god. Okay, the force is being applied on her feet, and that's what's accelerating things up. And work is force dot distance. So there's definitely a force there, but is there a displacement? There's no displacement of her feet. So that work has to be 0 because her feet aren't moving. And we'll see this in some more of the problems later. So if we're considering the woman in our system, this work is going to be 0. And anytime you see something like a E woman or E internal, you should think of like the extended system, and that your work is probably going to be 0 if the spot the force is being exerted on, if it's not moving. So what does this leave with us? If we look at what I just wrote, is that B? Looks like. What do we have? Yeah. Okay, B. Problem 13. We have a block. Oh God. Block. Mass A. Specific heat A. Initial temperature TA. And there's a second block. I don't know if it's bigger. I'm making it bigger. Mass B, specific heat B, temperature B. Okay. So let's say that, okay, let's do this. Yeah, okay. We're gonna do energy principle, delta E equals work, system, surroundings, 2 blocks. Let's put them both in our system. Surroundings, none. Okay. So, also, there's a part that I ignore on the. Actually, let's do this instead. Let's put 1 block. Let's do. We'll do block. We'll do A block, and then the B block will be the surroundings. It doesn't really matter how you set this up. This might be the most easiest to understand. So, in our energy system, I always have made kind of the approximation that Q just isn't there. But the full form is delta E equals work plus Q. So, here we go. So, if we make A block our system, we're gonna have delta E internal of the A block is equal to Q because work is 0. There's no moving parts here. Whatever change in internal energy we have of the first block has to be heat lost. And we know that delta E internal is equal to MC delta T. So what this is going to simplify to is heat lost by block A is equal and opposite to heat lost by block B. That's really what these problems are always going to come down to. Okay, so what is that going to look like? M of block A, C of block A, and then delta T of block A, that should be capital, is equal to MB, delta TB. Okay. And what are those delta T's going to look like? Let's sub in those. So here we know, since they're coming in contact with each other, they are going to have the same final equilibrium temperature. Their temperature final is going to be the same one. So delta T, it's TF minus TI, right? So we have that T as our final temperature minus the initial temperature of block A, which is just TA, equals MB T minus TB. Same deal for block B. Okay. Oh, and also there's a negative. Like I said earlier, it's got to be negative up front. And the way they set it up is they set them up on the same side. So if you just wanted to add over, block B, you could do that. E equals 0. Okay, so I just added that over that side. So what does that leave us with? Looks like A. Oh god, nice highlighter. There we go. Yeah, A. All right. Problem 14. You're trying to repeat an experiment, 1 kilogram water, and you stir it. So you're inputting work by stirring it, and it raises by 1 degree Kelvin. What is the magnitude of heat transfer from the water to its surroundings? Okay. Energy principle, delta E equals work. System, surroundings. So, okay. Water, U. In parentheses stirring, because you're going to input the work of stirring. So what is our delta E of the system going to look like? This is just going to be comprised of delta E internal, and then the work from stirring. And we know delta E internal is MC delta T, and we know the work of stirring is 5,000. And looks like we got everything to solve this now. 1 kilogram times 4,200 specific heat times 1 degree Kelvin. Sorry. Oh, and also there's going to be heat loss to the surroundings. Oops. There we go. So this is the full form of the energy principle. I just forgot the Q at the end, which is ironically what we're solving for. So we're going to get that. We're going to get 4,200 equals 5,000 plus Q. Q equals negative 800. That's 8,000. Okay, 800. And they want, so that's points to B, obviously, but our sign's wrong. Reason being they want the magnitude. And also, if you think about it, if Q was positive, it would mean heat was being added into our system. If Q is positive, it would mean it was increasing the internal energy of our system. If it's negative, it means it's taking out, which means heat flow is going from our water to the air, say, which makes sense. So Q should be negative, and they just want the magnitude, which leaves us with B, which is correct. Okay. We have a house. Okay. We have a volume of it, and temperature. You bring a closed bucket in. What will be the approximate temperature after reaching equilibrium? So here, like I mentioned earlier, in one of the problems, heat lost by the house has to be equal and opposite to heat gained by the bucket, we'll call it. So MC delta T of house equals MC delta T bucket, or water. So what is that going to look like? So this isn't actually of the house. This is of the air in the house. Air, and then like water. That's what we're analyzing. So what's the mass in the house? They don't tell us explicitly, but we know a volume and we know a density of the air. So how can we go from one of those to the other? We have a volume of 500 meter cubed, and we know that it's also 1.2 kilogram per meter cubed. So I like looking at the units here. If you multiply these two, you'll cancel meters cubed, and then you'll just get kilograms on top, which is what we want. We want mass of air. So multiply those. 500 times 1.2, 600. Let me scoot this over now. So we know the mass of the air in the house is going to be 600 times C. Specific heat of air is 1,000 times change in temperature, which we don't know. So I'm going to call, and again, here's our constraint to the problem here. They have the same final temperature. So when we do delta T, when we do T final minus Ti, we're going to use the same T for the bucket and the house. So T minus Ti, which is 0, they tell us up here, initial temperature of the air in the house is 0, equals mass of the water, 10 kilograms times specific heat, 4,200, times change in temp, which is, it comes in at 100. So it's got the same final temp, and it comes in at 100. So now we are looking for T. What's the approximate temperature in the house after reaching equilibrium? So let's solve this. So I'm going to start putting this into my calculator. Okay, this is just going to be 600,000 T, which equals 42,000 T minus 420,000. Wait, no, that'll be 4.2 million. Right? Make sure I got my zeros right. Yes. Yeah. Okay. Okay. Wait. That would give us a negative T. Oh, because I see why. Once again, I forgot. You got to add the negative right there. Okay. Because heat lost by one is equal and opposite to heat gained by the other one. So this is negative. This is positive. There we go. Okay. That becomes 642,000 T, which equals 4.2 million T final equals 4.2 million over 642,000, which is 6.56-ish. Not that one. No, no, no. E, none of the above. There we go. And you should have a calculator on a test to be able to do all that. Okay. A single falling coffee filter is falling with a velocity, reaches constant terminal speed. At this speed, how does the magnitude of force due to air resistance compare to the magnitude of force due to gravity? Well, let's do a force balance on this. So you got gravity pointing down, right? And we know that there's a drag force resisting it. So it's reaching constant terminal speed. At terminal speed, it's at the maximum velocity it can reach. So if it's at we know F9 equals ma, and if it's at max speed, it's no longer accelerating, which means a equals 0, which means F net also equals 0, and we know our F net is just F drag minus Fg, which equals 0. So Fg and F drag, they have to equal each other. So B. Okay. We got a spring of stiffness and unstretched length is placed on a horizontal surface. A block is put on top, pressed down, compressed, and then you release it. The spring pushes all the way up to the top, and it's launched into the air. Okay. With these problems, what they're testing is, can you set up the energy principle right? So let's see here. So if we just look real quickly at the answers, all three, Amy, Beth, and Kathy, they actually have all their equations are completely equal. If you can imagine, Beth, if you could imagine adding over her Ks value, it would be exactly the same as Amy. And if you subtracted over mg for Kathy, it would be the same. So how are some of these people wrong? It seems ridiculous, but the gist of the problem is they want to see if you can put things on the right side of the equation from this. So let's set this up like this. So let's define our system and surroundings. What they want to test is, do you understand that surroundings do work and that surroundings don't belong on like the delta E side of the equation? So let's see what they put in their system and surroundings and see if they're right. Amy has the block, and then earth and spring. So the block is going to have K tran. So the block energy is always going to be something like, well, actually they tell us half mv not squared minus 0, and then the earth is going to be mg L naught minus mgl. They're going to look something like this, just for reference so we know what we're looking at. Let's see, I'm going to use L. Shoot. Something like that. I'm just looking at for reference, so like when we look at this one, we know they're talking about the spring. So let's go back to Amy. Amy has the block, so that's the contribution from the block kinetic. That's good. Earth is on the right-hand side of the equation, which is good, because she said it was in her surroundings, so it should be on the work side. And then she has a spring, also on the right side, which is good, because she put the spring in the surroundings. So Amy looks good. Checks out. How about Beth? Beth has the block and the spring. So if we just move the spring over. Oh. Spring. Oh my. Okay. Beth has the block and the spring, the system, and Earth and the surroundings. So Earth, gravity, contribution, spring, and then from the block. So that also looks good. Let's see what Kathy's got going on. Kathy has contribution from the that's a highlighter. Contribution from the block kinetic on the left, gravity also on the left, and then she's got spring on the right, which she put nothing in the surroundings. So the spring contributions should not be on the right-hand side of the equation. It should be on the left-hand side. So Kathy, nope. This one says Kathy's correct, so no. Amy and Beth are correct. So no. It's got to be D, which is true. Nice. Max height. All right. Delta E equals work. That's going to be our energy principle here. System, surroundings. I'm going to put nothing. And then block, spring, Earth. So when we do our energy principles, we're going to be comparing two locations. And let's pick this. Actually, let me not do one. I'll do this as initial, this as final condition. Initially, it's got a velocity. Finally, since it's at that highest point, V final is 0. It's also a height H max up. I'm going to call this H equals 0. And the spring is completely relaxed in both conditions. So the stretch equals 0. So when I would have went earlier to do U spring, which is equal to half KS S squared, this is the stretch length. But in both of these conditions, S is 0. So that contribution is going to be completely gone. So let's take a look at what this is going to look like now. I'm going to do kinetic first. Final kinetic energy is 0 because it's not moving. Initial is half mvi squared. I think they call it v naught. Anyways. And then finally it's got mgh max. And initial, like I said, mg 0. So that's just going to be 0. Nothing in the surroundings. So 0 work. And then we've got negative half m v naught squared. I just changed it. I think they call it v naught. Yeah. Plus, I'm going to actually, this is just 0. Plus mgh max equals 0. I'm gonna move up here now. And I'm going to add over half mv naught squared. Half mv naught squared equals mgh max. M's cancel. What are we solving for? H max. So v naught squared over 2, divide over g. Nope, outside. H max equals, that's not how you spell max. H max equals v naught squared over 2g, which is correct. Epic. What is the time T max after it is launched to reach the highest point? Okay. Now, when we've been solving problems this entire test, you've been doing delta E equals work. No matter how we set this up, usually time's not going to come in as a factor. So let's introduce something not related with energy. Let's introduce the momentum principle from Unit 1. So change in momentum equals net force times delta T. Okay. And let's do the same thing we did in the last problem where we pick 2 points and then compare them and sort of do a balance. So Let's do the same two conditions. Let's do initial is this one on the left here. We use the same initial and then the same final. And then we pull up one more definition. Momentum is equal to mass times velocity. So we got mass velocity final minus mass velocity initial equals net force over the time, which, let's figure out what that net force is. The spring is not exerting any force because it's completely relaxed. Also, during this entire travel, it's not even touching it. So, no net force from the spring, but over this entire flight, gravity is pulling down the whole time. So let's make net force equal to mg. Mg times delta t, okay? And we know that final velocity is 0. It's not moving at the very top. So that's 0. And also, I'm going to swap again, negative m. I'm going to change vi to v naught equals mg delta t. Okay. And also, I keep forgetting these negatives. Net force, mg is in the negative direction. So you can cancel a negative. I'm not going to draw that, but you can cancel the m's. And this is going to become v naught equals g delta t. And we can divide over g. So delta t is going to become v naught over g, which gives us a, which is correct. There we go. All right. Problems 20 and 21. You've got a friend. They're crouched and then they're jumping. Okay, the feet never move from the ground, which is important. And there's a normal force, change in internal energy. Okay. So what do they want? Which of the following equations represents the energy principle of the point particle system applied to your friend? Okay. So in the point particle system, we only care about the center mass of the person. You can completely ignore this person as like a complicated, thing, and just think about them as one particle. Initially, where is his center mass? It's like right there. So let's say it's at that point. Okay. And then finally, after some time, his center mass is right there. What this H is representing, I believe. So his center mass moved along that distance H. So let's see here. We know delta E equals work. In our system, let's put the dude, the person, the friend. In our surroundings, let's put we're going to put Earth in our surroundings because I'm just looking at the answers. They put gravity on the right hand side. That's the reasoning there. So we're going to have delta K trans equals, since this is our point particle system, we're looking at the center of mass. And our center mass moved across this distance h. And the force was applied, the normal force pushing up was applied to the center mass that whole time. So that's going to get included in our work. So what is that going to look like? That's going to be F normal times h. There's also work due to gravity, which is going to be negative. Also work equals force dot distance. So I'm doing this. Gravity is pointing down the whole time, so that's going to be negative work. You're going to have negative mg, which is the force of gravity, times the displacement again, which is h. So delta k trans equals, you can pull out an h, normal force minus the gravitational force, which looks like c, which, let's see, is true. Also, for signage of work, I don't know if you could have gotten it wrong here, but if the reason our sign of gravity is negative is because it's pointing in the opposite direction as our displacement. Our displacement vector is going up, obviously, right? He's going upwards. Gravity points downwards. When your force vector and your displacement vector point in opposite directions, you're going to have a negative work. That's like a property of dot products, and that's why our normal force work, our work contribution from normal force is positive, because the normal force was up, and they're in the same direction. So if they're in the same direction, positive work. Opposite direction, negative work. Okay, problem 21. Which equation represents the extended system? So now we're not treating them as just a point in space. We're now treating them as the whole thing. Immediately, how is this going to change? Well, first of all, let's define things. System, person. Looks like Earth is still in the surroundings. I see MGH on the right-hand sides. Okay. So now we're considering the whole person. So now let's look specifically, where is the normal force being acted on this dude? It's being put on his feet, right? And as they mention, we're only looking at the point. Your friend's feet are stationary on the ground the whole time. So maybe I should draw a little bit of another picture. Initially, he's crouched, and then like he's fully extended. Okay, he just grew like 15 feet. It's okay. He's extending up. His feet are stationary on the ground the whole time. So even though there's that normal force, so work is force dot displacement vector. And yes, we have that normal force, but his feet aren't being displaced at all. So the work due to that like normal force, it's going to be 0. So immediately, nope. 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 So immediately it has to be B or E. But when we also do the extended system, we're going to add in the internal energy of the person and relative energy. So let's write that out. You're going to have translational kinetic energy still. And then you're going to add in these internal and relative terms. And then we have the same work due to gravity as before. Reason gravity doesn't change is because gravity acts on mass. And so it does always work through the center of mass of our person, which still moved through H. So that leaves us with B, which is correct. Okay. You hang by your hands from a tree limb. That's a height above the ground, and then you let yourself fall. You shock with your knees. You absorb the shock with your knees. And then you end crouch. Okay. What is the kinetic energy at the instant your feet first touch the ground? Okay, let me draw. So this is the final. This is like all the way at the end after you're crouched. Let me draw a little intermediate picture here. Yeah, we'll do that. So after you're falling, let's say you're going to keep this like exact same body shape. Because here your arms crouch down, looks like your legs get a little shorter, maybe like your knees, come in a little bit. Those all have delta E internal contributions. So let's consider a case where that's not happening. Right before you touch ground. This is the case they're looking for. Your arms are still in the air, your legs are fully extended. This is right before you touch the ground. You have traveled this distance D. So now D's up here, right? Okay. So let's use the point particle system because nothing's moving. So let's use our energy principle. Delta E equals work. System, surroundings. Okay. Earth, U, none. Okay. So our delta E then is going to be delta K trans plus delta U gravity. And there's nothing in our surroundings. Nothing's doing work. I'm going to do this over here now. Initially, we have no kinetic energy. velocity equals 0. Finally, we have, VF, which equals something. So final half mv f squared minus 0. Gravity, initially, let's make this h equals 0, like the ground. So, well, actually, yeah, we'll do that. Initially, you have mg, finally, you have mg h minus d height. So your center of mass is right here. And you were a height h, and you just took off d. So you're now a height h minus d off the ground. Initially, you were just mgh, and that all equals 0. Okay, so when we evaluate this now, mgh minus mgd minus mgh. Okay, those two are the same. Let's see, add over mgd, half mv f squared equals mgd. And cancel. What are we looking for? Oh, wait, we just want kinetic energy. Never mind. So this whole term is what you would call the kinetic energy. So mgd. Oh, I'm behind. mgd is our final answer, which looks correct. Okay. What is the change in internal energy in your body from the initial to final position? Okay, so let's set up our energy principle. Delta E equals work, system, surroundings. Okay, let's put everything in our system. So person, gravity, those are the only things contributing here. Oh, also I called it gravity this time, but gravity / Earth. Okay. Okay, now we can ignore this case where it was sort of like a intermediate. So still h equals 0. We're comparing the complete initial when he's hanging to the complete final when he's sitting there. So, what's the change in kinetic energy? Well, initially he's hanging, his velocity equals 0, and he's sitting here finally with velocity equals 0. I'm going to ignore k trans because it's not changing. How about gravity contribution? So we can have we're going to have a delta U grav term. We're also going to have delta E internal because you're going to have a delta E internal energy change when there's mass moving around of your person. Generally, you're going to see this in problems of people, such as limbs moving. When there's limbs moving, like they say in the problem too, his knees bend, his arms appear to be moving around. Whenever you have moving parts like that in your system, mainly human limbs, you're going to have an internal energy change. So we're going to have that contribution, and then I put nothing in the surroundings, so 0. So we just got to find out this term and then make it equal to the negative of internal energy. So change in U grav, what is it final? Final gravitational energy is mgb, it looks like. Because U grav is equal to mgh. Okay, and then initial is just mgh. So there we go, plus, I'll do, oh god, delta E internal equals 0. Okay. Add that over, delta E internal equals mgh minus mgb, which is, if you want to pull out mg, you just get h minus b, which looks like A, which is correct. Okay. Problem 24. using a string, you pull a box. It's full of liquid, so initially you got like liquid like this, and it's gonna kind of slosh. You're probably gonna get like a profile like that. So your center of mass is gonna change, which they tell us. Okay. What is the change in internal energy of the system? So, as you remember maybe from previous problems, internal energy changes are only accounted for in the extended system. So that would make you feel inclined to believe that we should set that up. So let's do that. System, the what is it? Water in there. The water, and then force. I'm going to say the force is in the force you're exerting is in the surroundings. So the only well, I suppose if we're doing the extended system, we're going to have a change in translational kinetic energy, and then plus delta E internal, and then this is going to be equal to our work, which is F dot D. And when we're looking at the extended system, we're not looking at the center mass. So even though the center mass only went through that distance, which is 1.75, the force was applied for the entire 2 meters. So our work on the extended system is going to be equal to the force times that full distance, which you're pulling with 100 newtons. 100 newtons times 2 meters. So, right, yeah, 2 meters. Okay, so the work is 200 there for the extended system. So we want the change in internal energy. We want this term. But in our current equation, we have 2 unknowns. So this is where we're actually going to need to pull out the point particle system. So this is our energy principle. God, that is bad handwriting. Okay, that's our extended system energy balance right there. Now let's take a look at the point particle. The point particle will tell us what delta K trans is so that we can subtract it over into the other side and then solve for ET, for E internal. So the point particle system, we got delta K trans still, but now we're looking at it as just a center mass. There's no change in internal energy. So what is our work of point particle system going to be? The force is the same, it's 100 newtons, but now we only care about the force that's been exerted through the center of mass, where the center of mass has changed, and it's only changed through that distance, and it's gone from 2.25 to 0.5. So that displacement is 1.75. So it's 100 times 1.75, which is 175 for our work. So now we know this. Now we know delta K trans, and if we come back down to our extended, we now know that 175 plus delta E internal equals 200. Subtract over 175, delta E internal equals 25. B. And there we go. Yeah. So with these ones, the extended system is going to have more variables in it, but you can use the point particle system to find one variable easier and then plug that back into your extended. The point is a more simplified system. Okay. Problem 25. So you've got a rod. The rod has no mass, and there's a string, and you're pulling on it with force. The balls fly down the rod, and the center of the disc has moved. Okay. Angular speed. So same thing as the last problem. We're going to need the point particle and the extended system. Since we know now that we got to use both, let's start with the point particle system so it'll be a little bit easier. So delta E equals work. Oh god. System, surroundings, like the system here. What do we want to call this? The disk, the object. The full object is that. And then the force. So if we're just treating this like one particle, initially it's right there with mass. There's being a force applied to it. It's ending up some distance d away. So delta k trans, which is all we're going to have in this simplified model, the only energy that's increasing is delta k trans. Delta k trans is then equal to our work, which is equal to the force vector dot displacement vector, which is just we're not evaluating anything here. Okay, so that's just FD. Okay, so delta k trans equals FD. Okay, now this is for the point particle. Now let's move into extended. Okay. Now we're going to have that same delta k trans. We're also going to have delta k rotational as well. Actually, that should be it. Yes. Okay. Equals force dot d plus s. Also, I don't think I explained in the last problem why I only picked FD. That's because that's where the center of mass moved. Now that I'm picking the extended system, I'm picking the full distance the force was acted through, which was d plus s. So now that we got that set up, we can evaluate these. So k tran is always half mv squared. K rotational is half. It's very similar. It's half I omega squared. There we go. Wait, I'd be forgetting something here. No, okay. Okay. Here we go. Okay. Change. Oh, we know what delta k trans is. We know it's FD plus, okay, let's say this now, half I omega final squared minus half I omega naught squared equals FD plus FS. FD's on both sides, cancels out. Okay. And we have no initial angular velocity. That turns 0. So half I omega F squared equals Fs. And they want omega F, basically. And they tell us the moment of inertia of this. So this I that I wrote, it's I of this system, of the whole system. And we need to evaluate that term out. So when you're looking for inertia for the entire system, you can sum up inertial contributions of the individual components. So for one, we're going to have this disk that's contributing some inertia, and each one of these little balls, there's 2 of them, is each contributing inertia as well. So what's the disk first? Let's do half mr squared. That's the disk. And then we have the 2 balls, which are, the rod is length L. Also, for any point, so say this is our axis of rotation. Say, well, I would just draw the example we got here. Rods, say I have some mass attached out here. The inertia for any mass attached in that sort of fashion is mr squared. It changes for what object it is. So for example, the disk is half mr squared. A point of mass is mr squared with no coefficient. So we know the length of a rod is L. That's going to be, so that means, inertia of the ball, I'll call it. The balls have mass little m, and then our radius is L over 2, right, because it's half. They're half that length. So eyeball equals ml squared over 4. So there we go. And we have 2 of these. There's 2 of those. So 1/4, what did I say, ml squared over 4. Yeah, okay. There we go. So the inertia of the system, half mr squared plus half ml squared. There we go. So now if we plug that back into there, we get half mr squared plus half ml. That should be squared. Omega f squared equals fs. This is kind of becoming a mess now. Okay. 2fs equals, okay, I'm going to times, actually by 4. If you just, yeah. 4fs equals mr squared plus ml squared. Okay, I hope that makes sense what I just did. Divide that over omega f squared equals 4fs over mr squared. That's mr plus ml squared. Square root both sides. And there we go. 4fs over ml squared plus mr squared. That leaves us with E, which is correct. Okay, problem 26. String is wrapped around an object, mass m, inertia I. You pull the string straight up. It spins faster, but it's not moving. What is the angular speed, omega, of the object after your height has risen some distance? Okay. Energy principle, delta E equals work. And let's pick our system and surroundings, object. And we're going to want to use an extended system here because we want angular speed omega. You don't consider k rotational in the point particle system. So let's pick the extended. In the surroundings, we're going to put the force of the string. So, okay. So what is this going to look like? We're going to have delta k trans plus delta k rotational, which equals work, which equals FD. Now, we know that initially you have velocity 0, initial, and final it's also 0. So delta k trans is just 0. And we know that k rotational is equal to half I omega squared. So let's set that up. Half I omega final squared. I'm going to call the final omega the final angular speed. I'm just going to leave that as omega. Minus the initial, which is half I omega naught squared, which they call it that right there. And then that is equal to force dotted with distance. So that would be y minus y naught. But if I'm just looking at the answers here, we can see in the answers, they're just going to define it as delta y, which is another way. So f delta y. Okay. Here we go. Times everything by 2, and then add over the other. Okay, times everything by 2, and then divide by I, and then add over the other term. So let's take it one step at a time. Omega squared minus omega naught squared equals 2f delta y over I, and you can just add over. Oh god, you can just add over the other one. Omega squared equals 2f delta y over I plus omega naught squared. Square root everything. Boom. If we look at our answers, they look a little bit different. We have f in our answer, and they have mg. Let's go up here. So we know an interesting thing about this problem is that it's not accelerating upward down. We know F net equals ma, and we know now it's staying stationary here. So we know acceleration is 0. Therefore, net force has to be 0. And net force is equal to, if we do our force balance, you got the F of the string pulling up, and then there's the F of gravity. So F string minus Fg, that's got to be 0. Therefore, if you just add over Fg, F string equals Fg, and Fg is mg. So we know the force of the string has to be equal to mg. Therefore, this equals 2F mg. Wait, no. 2 mg delta y over I plus omega naught squared. Oh, shoot. Okay, that kind of looks bad. Whatever. Which leaves us with A, I believe. Yes. Okay, A. 27 and 28. We got identical masses on a frictionless surface connected to each other with the spring. We have initial and final configurations. There's a force. Okay, change in translational kinetic energy. Easiest way to get translational kinetic energy. We got, what are the options? So when we do our energy principle, we can choose extended or we can choose point. Point is going to ignore a bunch of other contribution, but it's going to include translational kinetic energy. So it will be the simplest way to get it. So let's do point particle. System, surroundings, force, blocks. I'm gonna put 2 blocks plus the spring. Not that that's gonna matter. Okay, so we got all that in our system. Move this over. Give me room. Okay, and then we're doing the point particle. So we're going to have, on the left-hand side, we're going to delta K trans, and that's going to equal our work. And work is equal to force dot distance. And then in the point particle system, we care about the force that moved through the center of mass. So if we're looking at this system as a point particle system, we're only interested in the center mass. So where is the center mass initially? It's right here. So just ignore the left block, ignore the right block. We're just comparing this dot of mass to this dot. Imagine all the mass of the system is just right there at that point. That's what we're comparing. So the force that we're putting through there is 100 newtons. That's the same regardless of if you choose extended or point. And we want to look at this distance between center masses. So it looks like here, these center mass initially, it's going to be halfway between both. You got 0.03, and then this looks like it's going to be 0.1. So displacement, you're just going to do final position minus initial position, 0.7 times 0.7. Delta K trans equals 70. Wait. Oh, hold on. This, hold the phone. Hold on. Okay, this is 0.03, which means 0.07. This is 0.077. 7 joules. Let's see. Yep, 7 joules. Okay, 28. Change in internal energy. So now we know we can't use the point particle again because we want to account for the internal energy. Extended. Okay. So we still got K trans. And then we're also going to have an internal energy contribution. We also have a work. What is that work going to be equal to? So when we're looking at the extended system, we care about where the total distance the force was pulled through. So as opposed to looking at just the center of masses, which we did earlier, let's look at the full distance the force is pulled through. Well, where was the force pulled? It was pulled from the front of this block to this, right? It's being applied to the front of that block. How far did the front of that block go? Like they tell us. It's at or the block isn't stretching or moving, so we can just look at the back. It moved from 0.04 to 0.12. So the displacement that we're interested in here is 0.08. And it's still 100 newtons. So then we got delta K trans plus delta E internal equals 8. We know delta K trans is 7 from last problem, so let's just sub that in. Delta E internal equals 1 joule. D, which is correct. 29. Okay, 4 objects of the same mass. They're in position on an inclined plane. There's a particle. They have the same radius. Okay. Which one's going to reach the bottom first? Okay. So, at the top, let's consider this. At the top, what type of energy do we have? I'm just going to say in our system, object, surroundings, none. At the top, what type of energy do we have? All the energy for all these is mgh. And at the bottom, it's going to be some combination of K trans and then K rotational. So, you want a really high contribution from K trans. But since, let me back up a little bit. Maybe not that much. Okay. So, they all have to have the same final energy. And their final energy is going to be comprised of these two in some combination. And we know that these two look something like this. Half mv squared plus half I omega squared. The only thing that's going to get you down the plane faster is your linear velocity. That's what's actually moving you down the plane. And since these have to sum always to mgh, you want a really big contribution from this one and a smaller contribution from that term. So you want a small inertia. So if we look at our inertias up here, we're going to want the smallest one, which is, it goes like this. And what about the particle? So we know the hoop's probably going to be the biggest. The hoop's probably the last, so no. Hoop, cylinder, sphere, and then what about the particle? The particle, it's flat. It doesn't, okay. The particle doesn't slide at all. So the particle has a 0 rotational energy and complete translational, which is what you want. That would get you down the fastest because it would have the greatest linear velocity to get it down to the finish line the first. Also, another way of thinking about it, inertia is sort of resistance to motion. So if you have a ton of inertia, it's going to move really slowly. Okay, so B for that choice.